Hello! In this video, we are going to prove the following theorem. Suppose tilde is an equivalence relation on A. Then for all x and y in A, x is related to y if and only if the equivalence class of x and equivalence class of y are equal. Now, since tilde is an equivalence relation on A, this means that tilde is reflexive, symmetric, and transitive. Now, since tilde is reflexive, or reflexive on A, this means for all x in A, x is related to x. Since tilde is symmetric, this means for all x and y in A, if x is related to y, then y is related to x. Since tilde is transitive, this means for all x, y, and z in A, if x is related to y and y is related to z, then x is related to z. Now, since tilde is an equivalence relation on A, this means every element of A has an equivalence class, and it's represented as follows. For each element x in A, this set is the equivalence class of x. It's the set of elements m in A with a property that x is related to m. And this set is equal to the set of elements m in A with a property that m is related to x. The reason why these two sets are equal comes from the fact that tilde is symmetric. Okay, so now let's get into proving this theorem. Now, we're trying to prove a statement regarding every two elements in A. So let's give ourselves two arbitrary elements in A. I'll call them x and y. From here, we want to show that x is related to y if and only if the equivalence class of x is equal to the equivalence class of y. So we're trying to prove a statement containing if and only if. So what we're going to do is we're going to prove if this is true, then this is true. And then we're going to prove if this is true, then this is true. Let's start out by proving the forward. We're first going to prove if this is true, then this is true. And to prove that, suppose x is related to y. From here, we want to show that the equivalence class of x and equivalence class of y are equal. And to show that these two sets are equal, we're going to show that the equivalence class of x is a subset of the equivalence class of y, and we're going to show equivalence class of y is a subset of the equivalence class of x. So to show that the equivalence class of x is a subset of the equivalence class of y, let's give ourselves an arbitrary element of the equivalence class of x. I'll call it p. What does it mean for p to be an element of the equivalence class of x? Well, if we take m to be p, it means that p is an element of A such that x is related to p. Now, since x is related to y, then using the fact that tilde is symmetric, this implies y is related to x. And since y is related to x and x is related to p, then using the fact that tilde is transitive, that implies y is related to p. And this tells us that p satisfies all the requirements to be an element of the equivalence class of y. Because if we substitute x for y, then the equivalence class of y is the set of elements m in A such that y is related to m. And if we take m to be p, well, we know that p is an element of A. That's what we have here. And we know that y is related to p. That's what we have here. So p satisfies all the requirements to be an element of the equivalence class of y. So we can conclude that p is an element of the equivalence class of y. So we have shown if p is any element of the equivalence class of x, then p is an element of the equivalence class of y. Therefore, the equivalence class of x is a subset of the equivalence class of y. So now, let's show that the equivalence class of y is a subset of the equivalence class of x. To prove that, let's give ourselves an arbitrary element of the equivalence class of y. I'll call it q this time. What does it mean for q to be an element of the equivalence class of y? Well, if we take m to be q, it means that q is an element of A such that y is related to q. But then, since we know x is related to y and y is related to q, then using the fact that tilde is transitive, that implies x is related to q. And this tells us that Q satisfies the requirements to be an element of the equivalence class of X. Because if we take M to be Q, well, we know that Q is an element of A. That's what we have here. And we know X is related to Q because that's what we just showed. So Q must be an element of the equivalence class of X. And so we have shown if Q is any element of the equivalence class of Y, then Q is an element of the equivalence class of X. And therefore, that tells us that equivalence class of Y is a subset of the equivalence class of X. And now that we know that the equivalence class of X is a subset of the equivalence class of Y, and the equivalence class of Y is a subset of the equivalence class of X, well, that tells us that the two sets must be equal. And so, this proves the forward direction. We have proven if X is related to Y, then the two equivalence classes are equal. Now let's prove the other direction. We're going to prove if the two equivalence classes are equal, then X is related to Y. So to prove that direction, suppose that the two equivalence classes are equal. From here, we want to show that X is related to Y. Now, using the fact that tilde is reflexive, we know that this statement works for every element in A. So in particular, it must work for Y. So taking X to be Y, we have that Y is related to Y. But this actually tells us that Y must be an element of the equivalence class of Y. Because if we take M to be Y, well, we know that Y is an element of A. That's where we started with. And we know that Y is related to Y because that's what we have right here. So we can conclude that Y is an element of the equivalence class of Y. However, since equivalence class of X is equal to the equivalence class of Y, that tells us Y must be an element of the equivalence class of X. Well, what does it mean for Y to be an element of the equivalence class of X? Well, if we take M to be Y, it means that Y is an element of A with the property that X is related to Y. So, X is related to Y. And that's exactly what we wanted to show. So, we have shown if the two equivalence classes are equal, then X is related to Y. And so, we have proven both directions of the if and only if. So we have proven this entire statement. And we have proven this statement given two arbitrary elements in A. Since these two elements of A were arbitrary, this means we have shown for every two elements of A, this statement is true. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.